Yeah, so thank you very much for the introduction and also for inviting me to speak at this conference. I mean, of course, it's no way comparable to sit here in rainy Cologne than sitting close to the ocean. Anyways, it's a pleasure. I'd also like to thank my collaborators. So that's these gentlemen down here, my previous PhD student, Ori Alberton in particular, and also Michael Buchholz, who's really driving the progress on this line of research. Okay, let me start very basic. It will be about these measurement-induced phase transitions. And the very basic starting point is really coming from quantum mechanics course. And so there we learn essentially that there's two fundamentally different types of quantum dynamics, a deterministic and a stochastic quantum evolution. The deterministic one is the one that we generate by Schrödinger equation. But then the other one, the stochastic one, pops in when we observe the system. So if we do a measurement on the quantum system, then the wave function collapses into one of the eigenstates of this measurement operator, of the observable that we're looking at. And the stochastic element is encoded in this probability object. And so that stems from the overlap of the current wave function with a measurement eigenstate into which we collapse. And you can clearly see that this dynamics is non-trivial if the eigenstates of the Hamiltonian and of the measurement operator do not coincide. Yeah? Because in that case, whenever we collapse into a measurement eigenstate, the Hamiltonian will just take us out there. In other words, the interesting situation is the one where these operators here don't commute and compete, yeah, by non-commuting. Now that in turn is of course a situation that is very well known from many body physics. Yeah? The situation of two non-commuting operators can give rise to quantum phase transitions. So here the situation is just we have two pieces of a Hamiltonian, where each of which wants to stabilize a ground state, say, with a different symmetry pattern. And if they don't commute, then there is the chance that we encounter a quantum phase transition at a finite competition ratio parameterized by this dimensionless parameter here. So that is, for example, the situation that we have in this paradigmatic mod insulator to superfluid transition, where the competition is simply between kinetic and potential energy of potential energy of interactions. Now, the question we want to follow here is when we now look at measurements in the many-body context, will we encounter similar singularities, similar phase transition type scenarios? And obviously, we're not the first to look into that. It was pioneered, or asking this question was really done for the first time in these two pioneering works here, where what people did is just to study the competition of an entangling dynamics. In that case, what they looked at is entangling random unitary circuits, which are interpierced by this completely local measurements by non-commuting observables. And the basic picture that was obtained in these works is put here. So the competition is essentially here, this dimensionless parameter, the number of measurements over time versus the number of unitaries that you throw per time unit. And the physics is clear in the two extreme cases where we don't measure at all. So that's this point here, where these random circuits have the property of generating chaotic dynamics, leading to a volume law entanglement growth. On the other hand, if we don't have any unitaries, then these completely local measurements, like a measurement of a sigma z, they will just collapse us into a product state of some random choice of these sigma i's here on each side. And such a product state, of course, has no entanglement, and that would in one dimension just be given by an area law growth or saturation of entanglement. What these works here remarkably established is that there is indeed, as in a quantum phase transition, a critical point at some finite competition ratio GC, which interpolates between a phase with a volume law growth and this area law entanglement growth. And for this intriguing phenomenon, several beautiful pictures, physical pictures have been developed. For example, the quantum error correction perspective, which we heard already in Eyol's talk on Monday, so in this work here and also in these works. Then another perspective on that is this so-called purification transition, where one asks, so if we start with a mixed quantum state, does the dynamics then actually lead us to a pure state, as we expected in the pure measurement dynamics, or not? Yeah, when the Hamiltonian is too strong, then we would always stay in the mixed state. And also, people have looked into mapping these circuit problems here into stochastic, into statistical mechanics models. So what I want to do here is to look at a slightly different model, which doesn't come with these random circuits, but rather kind of physically motivated dynamics of locally monitored fermions, just hopping around on a chain. In this context, I would like to point out that there's a kind of new type of entanglement phase transition, which doesn't go from volume to area law, but actually from a critical scaling phase, so the logarithmic growth of entanglement entropy to an area law, and provide some physical understanding of this phenomenon in terms of an effective field theory for a continuum limit of this lattice model that we first analyzed numerically. And then I point out a little bit of an outlook of things that we were doing in the meantime, if someone has maybe already heard this talk, so at least in the end I have a little bit of new stuff. Okay, so here is the model that we're looking at. It's extremely elementary. We have a Hamiltonian which induces entanglement growth by just hopping particles along a one-dimensional lattice with a hopping strength J, and we put this into competition with the monitoring dynamics of locally determining the particle number density with the strength gamma, which of course will also, because the process is entirely local, lead to entanglement separation. Now, in technical terms, we are not looking at these projective measurements that have been mostly looked at previously. We're rather looking at the opposite but smoothly connected limit of weak continuous measurement. And such a process here is described by a stochastic Schrödinger equation. Yeah, so this is also called quantum state diffusion equation. The stochastic element here that replaces essentially these measurement probabilities is encoded in this Gaussian white noise variable here. And the competition in this case is now realized as principle as before by this rates measurement versus hopping strength. And to understand this problem qualitatively, let's again look at these extreme limiting cases. If we only have unitary dynamics found here, so only this Hamiltonian, and we compute the entanglement entropy as prescribed here. So we take a portion of the system, trace out this part B, and then look at the entanglement, at the entropy of this remaining subsystem density matrix. We find it's a volume law. So in the opposite limit, where we only have measurements, then it's a good point to specify these measurement operators that come in here. So you see they involve the local density operator. And to give you a little understanding of this equation, it's useful to realize that it describes a continuous collapse of the wave function. Yeah? You can clearly see that all these terms here, so including this multiplicative noise term, they stop acting when the system actually finds itself in a local number eigenstate, fulfilling this condition here. And that's exactly what you expect. Yeah? When the system collapses into a number eigenstate, then the evolution stops, yeah? In the absence of a Hamiltonian. And clearly, we have the same picture as before. So there's no entanglement in such a product state, and we'll get away with an area law entanglement. There is the caveat, and conceptually, it's really the same thing as in these random circuits. Psi, the stochastic Schrödinger wave function here, is a random variable. So we need to really do some statistical analysis. We need to look at the trajectory ensemble to extract any meaningful physical information. And so that is, here comes a big problem. Yeah, so then of course the solution. So if we look at usual observables, we immediately see like this quantum average here without averaging over the stochastic realizations associated with measurement. Then we see that's linear in the state, as in, or more precisely in this trajectory state projector rho. And if we then average over all the trajectories, we do the statistical average, then we'll get something here linear in this averaged projector. The problem is then that these Hermitian jump operators or these Hermitian measurement operators, they will make this average state here just look like an infinite temperature state. And from that, you immediately see there's no interesting information in anymore. So to circumvent that problem, one can, as a next best guess, look at state-dependent observables, like signaled here. And that's more promising because of this relation. The function of an average is not the same as the average of the function if the function is indeed nonlinear. Examples of such a circumstance are obviously the von Neumann entropy, where the observable, if you like, the Hermitian operator of which we look at the expectation value, is extremely nonlinear in the state. But a next best guess, maybe less greedy, is to look at correlation functions which are just quadratic in this state projector. So each bracket here means that there's one power of this operator of the state projector occurring. So with this in mind, I would like to come to the trajectory, to the phase diagram that we find for this model. And the most important axis is the asymptotic thermodynamic limit, which is down here, where here we have this competition of measurement rate versus hopping strength. So in this limit, in the asymptotic limit, we find here a logarithmic growth of the entanglement entropy, which already signals somehow a critical or a gapless phase for this problem. And I have more comments on that later. Here's just the phenomenology of a log growth of the entanglement entropy, while if we strongly monitor the system, then we find this saturation to an area law. Now, possibly interesting is this point down here that I was already mentioning. In the system without any measurement, we find this volume law entanglement growth. And that's indeed confirmed in this phase diagram here. This is essentially inverse system size. And if there's a non-commuting limit going on in here, if we ramp down, if we go to the thermodynamic limit without any measurement down here, then we'll always stay in this volume law phase. Conversely, if we approach the problem from that side, from very large system sizes, then we'll always find this logarithmic growth. And so that's a thing to keep in mind, that here's a kind of crossover between volume law looking behavior and this logarithmic asymptotic behavior. Okay, now let's characterize this phase here a little bit in more detail. And there's several ways how we can find out about that. One way is to look really at this averaged entanglement entropy. We can fit our calculated entanglement entropy to this Calabrese formula here. And we then are interested in this central charge, which is usually the central charge in say, a Lattinger liquid or conformal field theories. Now, in our case, this conformal charge is only an effective conformal charge, and it actually strongly depends on the measurement rate gamma and has this intriguing jump-like behavior when we really approach this transition point here. So this is reminiscent of a BKT transition, and I have some more comments on that later on. So on the other hand, we also see that this connected correlation function, so this less greedy variant, just quadratic in the state, also is a very good indicator for this phase transition, in particular in this regime here, in the this gapless regime, we find here algebraic decay of this correlation function, while in the area law phase here, it's an exponential decay. For the experts, there's also a kind of emergent conformality scenario, which is witnessed here by this mutual information and the collapse of these data points somewhere here, taken somewhere here, the critical phase here indicates that the long wavelength theory actually has this emergent conformal feature. Okay, instead of looking at the phenomenology here in even more detail, I'd rather give you a flavor of how we can understand this phenomenology based on an effective field theory for the problem. And to prepare for that, I would like to start with a really simple toy model that really hosts basically the intuition for the many-body problem as well. And that's just a single fermion hopping on two sides, equivalent to a two-level system, which we let undergo this measurement dynamics here. So if we switch off the hopping, the Hamiltonian, then we collapse continuously into the eigenstates, and we will either see the particle on that side or we'll not see it. Now, put a little bit, so the system then collapses to one of the eigenstates of the measurement operator. Now let's put on a little bit of hopping between them, and you see that the system remains pinned to the eigenstates of the measurement operator for long times, and only in short instanton-like transients it really changes the eigenstate from time to time. And that's a kind of pinning scenario for pinning to the eigenstates, and that is really opposite to the weak monitoring regime, where essentially only vanishing time is spent in the eigenstates. Instead, the system is almost always in a superposition and undergoes basically these Rabi oscillations of the unmeasured dynamics. Now, the point is that although we have these qualitative strong differences between these two cases, this is really invisible. All this intriguing difference in physics is invisible in the linear averages, but it is seen, for example, in this quadratic covariance matrix. That's essentially the two-side version of the correlator that we used previously to detect the phase transition. Okay, so, and that gives us then the guiding picture for devising an analytical approach to this problem. So we want to look at a situation in the thermodynamic limit where we have essentially the chance that, that this smooth feature here acquires some non-sharp non-analyticity and would signal a quantum phase transition.
3 minutes, Sebastian, 3-4 minutes.
Okay, okay. Good. So we look at the minimal model in the continuum in 1+1 dimension, and we keep in mind that we need to have this essentially nonlinear correlators, which we address by a replica construction. The main insight from this construction is that this replica degrees of freedom host a non-Hermitian sine-Borel model, which in fact tells us that there is a pinning transition, and it is in the PKT universality class. So let's go through this quickly here. So we essentially can understand this long wavelength model as a naive bosonized version of our lattice model. So then we end up with this Dirac Hamiltonian for the Hamiltonian part, and that is of course equivalent to a Latinger liquid with phase and density fluctuations. The measurement operators, they split up into two parts, which they are represented in fact by a current operator in this Dirac theory and a vertex operator. And if you bosonize these terms, the physics really becomes transparent. So these the current operator becomes a linear and gapless operator, but the vertex operator really becomes a nonlinear function of this density fluctuation field phi. Yeah? So among them they commute, that's clear. But they don't commute with the Hamiltonian with the phase fluctuation part here. Okay, let's now think how we can access this quadratic or this nonlinear in the state a correlator here to produce such a nonlinear in the state object here, or a correlation function. We can just replicate the wave function in Hilbert space, so we just take two copies of them. And all the quadratic in the state observables like this one here are then encoded in the linear statistical average of this replicated density matrix. Yeah. So that's the object of interest. And in fact, we are interested in deriving a quantum master equation for this replicated and average state. And it looks like that. There's from each of the copies one individual heating term coming that looks like a Lindbladian, but from the replica, but there's also a coupling of the replicas to each other, which introduces a new term, which doesn't have a Lindblad equivalent. And the key to this problem was really to realize that we better change coordinates in this replica space. We go to an average coordinate and to a degree of freedom describing the fluctuations in between the replicas. And if we do so, then this master equation becomes separable. Yeah? Without looking much at the equation, the important point is that the average coordinate, in fact, heats up to infinity, that gets all the noise. It only has a jump term here, while this relative coordinate really cools down into a dark state. And so we can then look at this relative coordinate equation here in particular, and we can see that it can be further separated into a pure non-Hermitian Schrödinger equation, an object of this term, which describes really the cooling into some dark state, some ground state. And the effective Hamiltonian that pops up here, in fact, takes the form of a non-Hermitian variant of the Sine-Gordon model, with the depinning term here and the pinning term encoded in the measurement nonlinearity. And we can extract the physics by just putting this non-Hermitian Schrödinger equation in a path integral formulation. And then the action for this object is displayed here, a non-Hermitian Sine-Gordon action. And the studying the RG flow for this problem leads to the following two observations. The flow at the short distances is actually modified because we have this complex parameters here, which is unusual. So that will introduce shifts in the phase border and in the phase diagram compared to the Hermitian case. But at long wavelengths, intriguingly, we see that this standard BKT flow is actually approached. Yeah? So we expect the same wavelength properties as in an ordinary BKT transition. And the resulting phase diagram that we construct from this theory here is this. We find an algebraic decay phase at weak measurements with the correct exponent, also found in the numerics. We find this phase with an exponential decay, which is the pin phase with exponential decay of correlation functions, and the critical point, which is in the BKT universality class, and that really fits very nicely with a numerical analysis of the scaling collapse of this effective central charge here, which really also exhibits a BKT scaling behavior. So that's also numerically confirmed. And now, of course, the grail is the entanglement entropy calculation. I'll keep this really brief. So in short, we have these Renyi entropies, which involve the nth moment of this trajectory projector here. And the von Neumann entropy is the limit n to 1 of this formula. But we have to introduce here the upshot, a general n replicas instead of only 2 as previously. And that we do it in a Keldysh theory, Keldysh replica field theory. The entropy can be really straightforwardly computed by modified boundary conditions. I'm coming from here. But the key message is that also in this n-fold replicated system, we observe this intriguing decoupling mechanism. Yeah? So the noise, so this is a field configuration for different replicas as a function of time, and the noise hits all these replicas in the same way, which suggests immediately to introduce a Fourier transform of it to see that really there is a kind of winner takes it all or loser takes it all phenomenon. One gets all the noise and all the other modes are completely pristine and don't see the noise. Yeah? And that actually makes it possible or reduces the entanglement calculation to just really a ground state calculation of the entropy because the zero mode actually doesn't enter. Okay, and from that we really reproduce this log scaling phase. We get the area law phase, and yeah, so that confirms again the numerics also in view of the entanglement entropy. Now, very briefly, a few other directions. You can ask, for example, in models of this class, can we get some different entropy scaling? So in the beginning, we were looking for some volume law. What comes out, for example, if you put a long range hopping, is actually a sub volume law scaling. So it's algebraic scaling, but not with the power 1, but rather with a power that saturates at 1/2. We also looked at different competition patterns, and in fact, you can have a dual scenario where essentially a critical phase is stabilized by some engineered dissipation, and an area law phase is then actually induced by a Hamiltonian. So it's kind of opposite scenario. Now, more recently, and that's really interesting developments, I think, is we are looking at these measurement induced phase transitions when there is a Hamiltonian that is really manifestly many-body chaotic. Yeah? And there, actually, a beautiful ordering principle emerges due to the strong decoherence that such a Hamiltonian has as a property. And finally, we also look in the direction that Ehud was presenting, namely in the presence of decoherence or the effect of decoherence in these systems, where we then have where we find that also this similar to Ehud's result, that and also to this work by Lee and Fisher, that there is essentially this phase, even if it's gapless, it's actually quite robust against decoherence. So with this, I have all these, let's call them backup slides. And here's my conclusions. Thank you very much for your attention. So if you have any questions, very happy to.
Thank you, Sebastian. So we have 5 full minutes for question. I see Ehud activating. Please, Ehud, go to the microphone and try to.
So maybe I have a question and a comment. So one question is, it wasn't clear from your bosonization type approach how interactions would come in, because interactions I would expect would bring about a volume law phase.
Interactions. I mean,
yeah. So how would change the picture?
I mean, interactions could, in principle. Let me just find the slide. I mean, so that's the structure of the problem that we get here, and this nonlinearity is really coming from the from the measurement operators. Yeah. But now what is interesting, and I think that's a specific feature of this problem, yeah, is that there is, I mean, we have different replicas, and within each of the replicas we have 2 contours. Yeah, so that's a forward-backward evolution that we always need. And this problem here does not show any coupling between the different contours. Yeah. So I think a volume law would show up as a coupling within each replica between the contours. And so that's usually how you describe thermalization, or how thermalization pops up in this Keldysh-like theories. Yeah, you generate essentially dissipation by coarse graining, and this dissipation then couples the 2 contours. Yeah? And I think it's maybe has to do with the deeper structure of this problem, that it's in some sense integrable. There's work by Fabian Essler, so that when we only have this density type operators and a free Hamiltonian, then there's
what I mean is, if you add, suppose you add 4 fermion interactions that make it
right. I mean, adding 4 fermion interactions would give us a Fermi-Hubbard model, spinless fermions. The bosonization would still look the same. It would have a different K parameter. From that, I would still expect we don't get, if we add here 4 fermion interactions in our spinless fermions, I wouldn't expect that we see any thermalization. That was actually one motivation to look into this adding a bath, to induce some coupling between these contours, because I think that is indeed the mechanism that would immediately give us a volume law. But the kind of dissipation or decoherence that we look at so far, really similar to what you're doing, that doesn't yet do the job. Let's put it like that. That doesn't lead to this coupling. It leads to other effects. But
this is very puzzling, because for example, in Majorana picture, if you have a non-charge conserving model, which we've looked at, then if you add interactions, it breaks a U1 symmetry, which gives you a power law phase, like you have. It breaks it down to Z4 or D4 that would have a broken symmetry phase in our picture, and it would give immediately a volume law phase. So it makes me a bit uneasy that maybe the U1 symmetry you have that kind of is responsible for the it's really the charge conservation but it seems to me that it's not the proper symmetry for describing entanglement dynamics, because there is some emergent symmetry associated with replicas that becomes discrete when you add 4 fermion interactions. That's what confuses me. And maybe that has to do with your, my other question about your, maybe I shouldn't, let me ask you after, because there are other questions. So
yeah, sure. I
wanted to hear more about your robustness to
special
dissipation and whether it's in bulk dissipation or only if it's in the edge.
No, we're looking really at a kind of scenario of imperfect measurements. Yeah. So where so imperfect. So that would be just adding some sigma z dephasing in your language.
But then you always have volume loss. So how can anything be robust? I mean, okay.
No.
Yes, let's go.
I mean, this is we do the honest numerical analysis, and this gapless phase is stable. I think it has to do with the fact that somehow, I mean, one thing is crucial here: the measurement operators and the dephasing operators, they commute. Yeah? So they essentially stabilize the same physics. And so that's a scenario of imperfect measurement. It's not the most general type of open system that one could look at. Yeah, I agree that it's another interesting direction. That
you still have an area law phase in this case?
Yeah, absolutely. Yeah. So I mean, I have some already.
You have to pass the ball.
I mean, area law. I mean, yeah. I think we also maybe someone else wants to ask something.
How can you have an area law if you have local dissipation?
Guys, sorry.
Yeah.
I would I mean, my style is to let true questions happen, like this one. So I would like Mike to unmute himself and have the same type of space. So Mike, you can take it over.
I don't know if this will be as interesting a discussion, but I wanted to understand what we can learn about the phase transition, because I guess if I understood correctly, the n=2 replica case as a BKT transition, you didn't say what happens at higher n, but then as long as when I take the replica limit, all of a sudden I get the CFT back. Can you help me to understand what we can understand about the phase transition from the replica trick?
I mean, so what we can do is to look at this scenario at larger n. Yeah? And in fact, I mean, it just gives you some prefactors which would not, as far as we see, would not modify the location of the critical point. But essentially, I mean, for each of the n's, we get the same BKT transition in this scenario. So we looked at that different n, and there's no qualitative effect coming from that. No.
Okay.
That was amazing fast, so that Taron can ask his question if it is quick.
Sorry, is it my turn or someone else?
Yes, it's your turn, Taron. Go ahead.
Sorry. Yeah, so the question I had was, I think it's more like it's more like a comment or based on Ahud's question. So to get the volume law, you don't even need interaction, right? And with non-Hermitian systems, you can have even volume law in free fermions. You can have volume law to log scaling. So I was confused.
Right. I mean, so this volume law, we have it at the unmeasured point. Mm-hmm.
No, even with measurements, it's not. I mean, if I post select on trajectories which have no jumps and have only non-Hermitian Hamiltonian,
okay,
and then you can have a transition from a volume law to log without any interactions.
At a finite strength, you're saying? Yeah,
I'm not talking about.
I mean, it's a different story. We're really looking at the ensemble of trajectories. I mean, this post-selection that you do, if you look at just the no jump evolution, is somehow it's an exponentially rare event. Yeah? So the one that exactly has no jumps is exponentially rare. I doubt that it's entirely representative of the trajectory ensemble, and in particular also the physics is a very different one. Yeah? So if you jump around all the time and you're now selecting this one trajectory where there's no jump occurring, I would like to emphasize that there's actually quite some interesting work where I think there's no complete analytical understanding, but where the people with Marco Schiro, they find actually that in some, I think it's an Ising model that you can still fermionize, and they look at this no jump evolution, and they find actually from their numerics, where they study the trajectory ensemble, the same critical point as you get when you just naively analyze, essentially diagonalize your effective Hamiltonian, the one that you're referring to. gives you the same critical point, but I think there's no completely really deep understanding.
But going back to your problem, suppose at the very beginning, if I neglect the jumps, even then you get the same phase diagram as you argued because of the decoupling, right? Your H effective, if I
it's a bit more subtle. Yeah, okay. So it's not exactly so our effective Hamiltonian really is, if you go through it, is not exactly the effective Hamiltonian, which you can already read off from, I mean, what I said previously, when we go to larger replicas n, yeah, then there is an n dependence in this.
I understand, but if I had taken the original H effective, which so that your Lindblad has some H effective, and then you have. So if I just take the original one, is the phase diagram look similar?
Does it look similar? I mean,
is it the same transition from?
Yeah, also it's actually a really good question. We didn't look at this most naive case. It's actually a good point. Yeah, so I could imagine it looks similar.
Okay, because that's what
but it's, for example, I mean, where's the critical point, and that a very good point. Yeah?
Right. Yeah, that's what I was trying. I mean, at least my naive guess was that even though this post selection on that specific trajectory looks very special, it may not be that special, because if the phase diagram looks again similar.
Yeah, that's somehow. I mean, it's so right. It's compatible with also with this result by Shiro and others.
Right.
And there's also a work by Sarang and Michael Gallens that are, I think, argue in this direction. Actually, it's really a good question to explore in our context. It's really the simple exercise, the simplest to do, actually. Yeah. Okay.
Okay. Thanks.
Thank you, Sebastian, for motivating and engaging chat.